uh, we were talking about canonical form theory yesterday. The whole so let me just quickly review what we were trying to do yesterday. So we have vector space V over a field F, and we take T linear transformation. So it's an element of end V. And when we try to write a matrix for the linear transformation by fixing a basis, so by fixing a basis, we get matrix for T. But the problem is that we can get several matrices. So if I begin with T, and if I want to go to the set of matrices, so this is my matrices M and F. Uh, if I choose one basis, then I can get A. But if I choose maybe some other basis, let's say B dash, then I can get some other matrices A dash, and I can get several matrices for the same linear transformation, right? However, we know by the definition of base change that all these matrices are similar to each other. So we learned this that we know that A and A dash are similar. Then we ask the question that can we find a nice representative, right? Can we find nice and simple, whatever this means, nice and simple representatives for each similarity class. So you should know that we are trying to find the representative for each class. So basically, we are looking at one linear transformation, and finding this representative means you have to find a basis which will give rise to that matrix, essentially, right? So in this connection, we saw that some examples of uh, uh, what could be called nice and simple is certainly diagonal matrices. And in general, any diagonalizable linear transformation will give rise to a diagonal matrix. So let me diagonalizable linear transformation. That means that you can find a nice basis to get a diagonal matrix, right? This is what is the meaning of diagonalizable linear transformation. The important thing is to find this basis, which gives me this. So in fact, the interesting thing is that we can classify this kind of matrices only knowing some property of its minimal polynomial, right? So classification of diagonalizable would be that T is diagonalizable if and only if minimal polynomial of T over X is the product of linear factors, of linear polynomials or linear factors, right? And another example, we saw that you can think of nilpotent or unipotent matrices or transformations as something example of nice and simple. And we also have characterization for such things. So the characterization for nilpotent and unipotent are very similar. So I will write down classification for nilpotent. Classification for nilpotent, this would be so it's very nice. So I will write slightly different in different way. So suppose I want to my dimension of vector space dimension of my vector space is n. Then you write down a partition of n. N is, let's say, n1 plus n2 plus nr. Then I have a nilpotent matrix corresponding to this partition. So suppose uh, this partition, let's just write it as n1 up to nr. This nilpotent matrix would look like uh, something like block diagonal, where 0 on the diagonal and 1, 1, 1 above the diagonal and all other zeros. This is of the size n1 by n1. So this is n1 and this is n1. And similarly, a block for n2 and so on. Similarly, block for nr. This is how a general nilpotent element will look like. Up to a nice representative, that means up to conjugacy or up to similarity. So again, you see that to find a nilpotent, the only data required is that this partition. So I'm trying to tell you this slightly differently than what I stated yesterday, because this is like trying to write the same thing in combinatorial way. So sometimes it's easier to say this way. So the statement would be that for any nilpotent linear transformation n on vector space of dimension n, there exists partition of n like n1, n2, nr, and vectors corresponding to n1, vectors corresponding to n2, vectors corresponding to nr, which will give rise to these blocks. I will explain this in a while. What do I mean by saying that there is one vector for n1, one vector for n2, and one vector for nr? These are what is called cyclic vectors, and they will give rise to these blocks. Okay, so I'll explain that. I will also just point you out that here n1, n2, nr, they need not be distinct. They can repeat also. So there could be two blocks of the same size. So usually when we write partition, we will write it, let's say, like n1 is greater than n2 is greater than so on, greater than equal to nr, and which is greater than 0. Right? So this is how we write a partition. And if you are trying to understand unipotent, any unipotent will be also classified by a partition, where on the diagonal, instead of 0, 0, 0, it will be 1. So any unipotent is classified by a partition of n, and up to similarity. So if I want to write the complete statement, up to similarity. Right. So if I have partition n1 plus n2 plus nr, this is partition of n, then the corresponding nice representative of that class would be, I will again use a similar kind of notation, would be something like, again, block matrices. So the first block is of size n1. And this time the block will have this diagonal entries also 1, and 1 above the diagonal, and 0 everywhere else. So there will be this kind of blocks. So this will be n1 by n1 block, this will be n2 by n2 block, and so on. And last one will be nr by nr block, and everything else is 0. So you see, this is something very nice, that nilpotent and unipotent. So obviously, like, we saw yesterday that if I write any matrix in upper triangular or triangular form, on the diagonal you see the eigenvalues. So for nilpotent matrix, the eigenvalues are 0. So you see 0 on the diagonal. For unipotent matrix, the eigenvalues are 1. So you see 1 on the diagonal, right? So, and then we wrote down two theorems, uh, uh, basically saying that we can write any linear transformation using these kind of matrices. So the first was Jordan decomposition. So Jordan decomposition, I wrote two different versions. So for any linear transformation T in and V, we have additive Jordan decomposition, that there exists some diagonalizable matrix and some nilpotent matrix such that T is S plus N and they commute. S N is N S. Right. And okay, I'm just writing in short, so I'm not writing in complete detail. So this was the additive version. And then we had multiplicative version, where for any transformation which is invertible, so if I take T in GLV, then there exists diagonalizable and a unipotent, such that I can write T as S times U, and they will also commute. So this is same as U times S, right? So this says that the kind of matrices we have looked at above, diagonalizable and nilpotent and unipotent, they are good enough. I mean, they can give rise to all matrices basically. But remember this, that when I have a linear transformation T, and I'm saying that it is sum of nilpotent and semi-simple, it doesn't mean that nilpotent is the upper triangular of the kind I gave you an example, and semi-simple S is diagonal. It is diagonalizable. It may not look like a diagonal a priori, right? So that may not be correct to say that S is diagonal. S is diagonalizable, and they could be diagonalizable with respect to different bases. So you may not be able to get them simultaneously in a nice form. So this theorem doesn't tell you all that. Okay. So okay, and but then we can actually have better theorem. There are better theorems. So for example, we can talk about Jordan canonical form. So we can think of, so the statement I wrote yesterday, I also assumed that I'm saying this statement over algebraically closed field. So let me be precise. So in this statement, I assumed here in Jordan decomposition that F is algebraically closed. Although there is a version which, although these things can be proved in more general thing, but I will have to define what the diagonalizable means and things like that. So the more general definition of diagonalizable is what is called semi-simple. That's why I'm using notation S. But right now, let's not worry too much about it. So for example, F could be complex numbers. So this is certainly true for that. And then we wrote down this theorem, where actually we found the nice representative, which is called Jordan canonical form. So in this theorem, again, we assume that F is algebraically closed. For example, F could be complex number, is an example. And let me write this theorem once again, somewhat clearly and cleanly. This was like last thing I was writing yesterday. So let's rewrite. So what does this theorem say? That if you begin with, let's say, a linear transformation in and V, then there exists a basis of V such that the matrix of T looks like the following. So to define what it looks like, we first define what is called a Jordan block. So let's say Jordan block of size m with respect to lambda. Lambda is some scalar. This is a notation. So this is just a notation. So I write like this. So you put lambda, lambda, lambda on the diagonal and 1, 1, 1 above the diagonal. Even if you take 1, 1 below the diagonal, it's fine. Some books or some people take 1, 1 below the diagonal. Either notation is fine. So m by m matrix and lambda is on the block. So this is usually called Jordan matrix, elementary Jordan matrix or Jordan matrix. So the theorem will say that first of all, there is a partition of n, which is n1 plus n2 plus nr, and there is a further partition of each ni. So each ni is further written as, let's say, ni1 plus so on ni ki. This is again partition of each ni. So this thing is supposed to be a partition of n. This thing is supposed to be partition of ni. So for every ni, n1, n2, and nr, each one of them there is a partition. Then we can write j ni bar lambda lambda I, and this will be consisting of the Jordan matrices j n I1 lambda I and so on, j n I ki lambda I. This is again a notation only. So the final matrix, the matrix of T will be now this. So this is how the matrix will look like. J n1 bar lambda 1, j n2 bar lambda 2, so on, up to j n r bar lambda r. So let's take a look at this statement. This is quite interesting, and sometimes it's also confusing. Sometimes I have seen students miss this part, saying that, like, they think that there is a partition of n1 into nr, and that's it. Then you take the Jordan block for n1, Jordan block for n2, for Jordan block for nr. That's not correct. You have to say that first there is a partition of n, and for each, so this partition of n, n1, n2, nr, these come from this correspond to different eigenvalues, right? So there could be there are r different eigenvalues. In fact, this n1, n2, nr you can see in the in the characteristic polynomial itself. So if you look at the characteristic polynomial of T, and let's say this is minimal polynomial of T. So this will be x minus lambda 1, some power, x minus lambda 2, x minus lambda r. So what will be these powers, right? That should reflect in what we have got above, right? So the power of characteristic polynomial here, this will be exactly that n1, this will be exactly this n2, and this will be exactly this nr. So that is the first partition of n. So if you actually calculate the characteristic polynomial and then factorize it, then this n1, n2, nr you will get first. All right, and then after each, after you get each one of these n1, n2, nr, you will get further partition of each one of them. Right, for each block, for each eigenvalue, you can have further more than one cyclic vectors, which I'm yet to explain you. But this idea you saw in when I was trying to represent Unipotent matrix. So for each eigenvalue, there is corresponding, let's say, something like nilpotent. That means it will again correspond to a partition. So for each one of them, you have to write a partition again. Okay, and let's say this is some m1, m2, mr. And this M1, M2, MR will be reflected here in these partitions, which you obtained for NI1. The largest entry of this will be actually that MI in this partition. So in the partition of NI, the largest entry is this MI here. So MI is the largest part in the partition of NI. So I just want to say here that sometimes, in general in maths, when you see a theorem, there are two things. One, understanding the theorem and being able to apply it to situations whenever you need it. And another thing is that knowing the proof and knowing the details and all that. Sometimes there are some theorems for which the proof is less important, but their application is more important. And whereas there could be some situation where knowing the proof is actually useful. In this case, both is important. But I would say that the theorem is more important. Understanding the theorem and how to apply that is much more important than actually knowing complete detail of the proof here. So in limited time, whatever we have, we'll try to see how can we prove this theorem. Okay. So the first step in going to prove this theorem, so we will see how to prove this, right? But of course, I will not prove each step, but I will just outline you some of the steps, and certainly some of the important steps, which is useful on their own. We will write down the proof. So as an example, maybe I should just write down an example. This is useful. Can we apply Jordan decomposition, right? So let's do the simplest example, and I will tell you as an exercise to do the same thing for M3. So let's look at M2C, and what we are asking is that write down all possible Jordan canonical forms. Right. That means they will give representative for each of the similarity class here. Okay, so how do I apply that theorem? So I have n equal to 2. So I'll write, first of all possible partitions of 2. So partitions of 2 are 1 plus 1, and there is another partition which is just simply 2. But remember, for each part of the partition, I have to take again partition, right? So I make two different cases here. Then for one partition of 1 is just 1. So I cannot do any further partition here, right? So in this case, you'll see that Jordan block, each one of them are of size 1, and they correspond to different lambda 1, right? So this will correspond to lambda 1, this will correspond to some lambda 2, which is not equal to lambda 1, right? And you will see that the canonical form is simply this. For 2 equal to 2, now I have to write the partition of this. But I see that there are two ways of writing the partition of this, right? So 1 plus 1 and 2. Here it corresponds to simply one eigenvalue. So when I try to write the canonical form for this, the canonical form will be I have lambda and the lambda repeats, right? 1 1 block. But here I have to write a 2 by 2 block. So it will look like this, right? So the canonical form corresponds to these scalars, and they will look like one of these three different types. But scalars can change. Different scalar will give you different class. Okay, so it's not like any lambda 1, lambda 2 you put here, you get the same class. No, different lambda 1, lambda 2 will give you a different class. So keep that in mind. Okay. So the first step in proving these things is what is called primary decomposition. primary decomposition theorem. This is quite interesting theorem and not very difficult to prove once you understand the trick. The trick is also very, very useful and it can be used many, many times. So let's try to do this. Try to do this proof. So what is the primary decomposition? I begin with, of course, a vector space V over F of dimension n, and I have a linear transformation T in N V. So I'm not assuming here that F is algebraically closed. I can do this theorem over general case. We'll apply it to algebraically closed field as a corollary. So F, any field. Okay. So F is any field. So suppose I have the characteristic polynomial of T, which I write as a chi T x, is, let's say, so I write, this is a polynomial, so I write it as a product of irreducible polynomials. So let's say P1 to the power N1, P2 to the power N2, so P1 x to the power N1, P2 x to the power N2, and so on, PR x to the power NR. And then minimal polynomial is, it will involve the same irreducible polynomial. So it is P1 to the power, let's say M1, P2 x to the power M2, and so on, PR x to the power MR, right? So I have written there factorization as a product of irreducible polynomial where Pi are irreducible. So what is the statement? The statement says that then we can write V as direct sum of certain subspaces V1, V2 up to VR, such that following happens, such that let's write it as number one. Number one, T will map each of the subspaces to themselves. So they are invariant subspaces. These are T invariant subspaces. This statement also means that Vi is T invariant, right? Second thing is that if I look at T restricted to Vi, if I look at T restricted to this subspace Vi, let's call them Ti. Then I can think of T as T1 direct sum, T2 direct sum, Tr. Meaning I can think of them as if they're in different blocks, right? And moreover, characteristic polynomial of this Ti is exactly Pi x to the power Ni, and minimal polynomial of this Ti is exactly Pi x to the power Mi. All right, is this clear? So you see that this when I wrote characteristic polynomial for T as product of these irreducible polynomials, I can divide my T as a direct sum, so that if I choose a basis of V, where I choose the basis of V1 first and then V2 after that and then VR after that, then I write the matrix of T with respect to that basis, then it will look like a block diagonal matrix, right? I hope this is clear, that this is something confusing point. So let me just write here as an exercise for you, that suppose I have a linear transformation from V to V, and suppose V is, let's say, V1 direct sum V2, and T maps V1 to V1 and T maps V2 to V2. Then if I choose a basis of V1 first, so choose a basis in such a way that I have a basis of V1 first. So this is giving me V1. and then extend it to basis of V2, maybe some other, no, it's a direct sum, so there is no other vector, and then VR plus 1 up to Vn. Suppose this is generating, like this is a basis for V2. So if you try to write matrix with respect to this basis, you will see that this get maps to itself. So when you write a matrix of T, you will get some entry here, here, here up to R, but 0 after this, right? So it will come out to be in block. Up to here, you'll get like this. But when you go to VR plus 1, it will be combination of only this. So you'll get things here, and you'll get 0 here. Right? So this is what I'm trying to say. So if I write T as a direct sum of V1, V2, VR, right? Like we have done here. And then now I can choose the basis of V1, and then I choose basis of V2 and choose a basis of VR, which will give a basis of V because it's direct sum. And then try to write matrix of T with respect to that basis. Then I will get block diagonal matrices. So what's the advantage of this theorem? This theorem will reduce our proof for Jordan canonical form or any one of those things to look at the matrices on only these kind of blocks. So the matrices which have minimal polynomial and characteristic polynomial involving single irreducible polynomial. Because I can use this theorem to write as a block if I have different irreducible polynomial, right? So this is the great thing about this theorem, which will be used. So let's try to prove this. I said that the proof of this is quite interesting, and we should write some proof, and we can understand this proof somewhat easily. And it's quite useful. It involves quite useful ideas. So let's do the proof of this. So proof of primary decomposition theorem. Okay. So what I do is this. So first of all, I have to find what are these VIs, right? If you can make correct guess for these VIs, half of the job is basically done. So here is what I claim. So we define Vi to be kernel of Ti T to the power Ni. Even if you take Mi, it is fine. It will be the same. It will be the same answer. But either one you can take. It's no problem at all. Okay. So this is what I define to be Vi. Now I want to prove all those results for this, right? So okay, if it is not clear what is the meaning of this, let me explain a little bit. So when any question, anyone has any question? So I have a linear transformation T from V to V. Remember that this is supposed to be end V. End V is an algebra. That means T square, T cube, all these things make sense, right? In fact, I can multiply by some scalar here. So I can multiply by, let's say, some scalar C1 here, C2 here, and I can sum them up. So you see that when I'm given a T, I can substitute T in any polynomial. Let's say I am given a polynomial Ft, Fx. Fx is, let's say, 0 plus a1x plus some a L x to the power L, then f of t makes sense. So f of t will be a0 plus a1t plus al t to power L. This is also an element of end V, right? So as I explained here, it makes sense to take power of a linear transformation, which is basically just the composition of t with itself, right? So we have so this makes sense. And hence it's a linear transformation. And once I have a linear transformation, I can try to take kernel of that, right? So that is how the VI makes sense. I hope this idea is clear. That the PI T. This is a similar thing you do when you say Cayley-Hamilton theorem, right? So you have a polynomial. In that polynomial, you substitute a linear transformation or a matrix and say that the whole thing becomes zero, right? So that is what it means. So now, okay, this part is just an explanation. Let's go back to the proof. So I have now defined what I call subspaces. So clearly, Vi is a subspace of V, right? Vi is a subspace of V. After all, it's kernel of something, so it's a subspace clearly, right? We need to prove now several things. We have to prove that V is direct sum of Vi. So for that, I need to prove the intersection of any two Vi is zero, and we need to say that every vector can be written as sum of the vectors from this, right? We need to prove this thing. So let's do that. Uh, okay. So here is the interesting part which I wanted to explain you. So we need to prove V is direct sum of Vi. For this, we need to prove two things. One, uh, Vi intersection Vj is zero if I is not equal to j. Second, that if I take any vector v in V, then V can be written as V1 plus V2 plus VR. So these two things I have to prove. So this we have to prove. This is the question mark. So what we do, so here it is how we prove this. We look at so we want to prove that, let's say V1 Vi intersection Vj is zero. So let's take a vector. Let's take a vector V in Vi and a vector W in Vj. No, I have to take in the intersection, so I should take the same vector. So suppose I have vector V which is in Vi also, and the vector V is also in Vj, right? What does that mean? That means Pi T to the power Ni of the vector V is zero, as well as P j T to power Nj of V is also zero, right? Okay, this is what is given to me. This is what it implies. Okay, now look at the polynomial Pi x to the power Ni and the polynomial Pj x to the power Nj. Pi and Pj, they are different irreducible polynomial. So these are going to be relatively co-prime. So these are relatively co-prime. I am using very basic ring theory of polynomial. So what does this mean? If there are two relatively co-prime polynomial, there exists some other polynomial, let's say ax and bx, such that ax pi x to the power ni plus bx pjx to the power nj equal to 1, right? This is what we would do in very basic ring theory for polynomials. All right. So let's use this. So in this equation, let's call this equation star. In this equation, I'll substitute t. I substitute t, so I get an equation for t plus d t p j t to the power nj equal to, what is 1? 1 is the identity matrix. So I have to say this is identity. Now apply the vector v. So if I apply vector v on this, I apply v here, and then I apply v here. What you get? We have seen that this is 0, this is 0, this is also 0, and identity of v is v. So this will imply v is 0, right? Very basic ring theory about polynomials helped me to prove this very quickly. You can see that this is very easy to prove that. Okay, and now I have to prove that v is sum of v1 plus v2 plus vr. We need to find that also. Let's do that. A similar trick can be done for that also. So let me define this first. So I'll define the polynomial pi tilde x to be the polynomial chi t x, and divide by pi x to the power ni. So basically, this is going to be the polynomial p1 x to the power n1 up to pi minus 1 x to the power ni minus 1, and then I will miss pi, and then I'll get pi plus 1 x to the power ni plus 1, and so on, right? So if I look at now again, look at the polynomial p1 tilde x, p2 tilde x, and so on, er tilde x. These are co-prime. They can't have any irreducible polynomial in common. So they are co-prime. And again, the theorem of ring theory will say that there exists some, let's say, polynomial a1x, a2x, and so on, arx, such that I get a1x into p1 tilde x plus so on, arx, pr tilde x equal to 1, right? So suppose I take a vector v in v, now apply and I substitute t here and apply v on that. Okay, so I write down the equation a1 x, p1 tilde x. Sorry, I'm going to substitute t now here. So I'll substitute t here, and then apply vector v, and so on. art, er tilde t, and apply vector v equal to v, because this side is identity matrix. So I'll substitute that. Okay, so let's look at this equation very carefully. What can I say about this thing here? Right? Let's look at a1 t p1 tilde t of v. I want to define this, let's say, as v1. My claim is that p1 t to the power n1 applied to v1 is 0, right? So this is claim, because this will mean that v1 belongs to v1, which is a kernel of this thing, basically, right? And why is that? It's very simple, because if I apply p1 t to the power n1 on v1 and I substitute this in here, so I have p1 t to power n1 a1 t p1 tilde t of v, then I can write this as, so this is a polynomial, they commute, so I can take a1 t on this side. And if I take p1 t to power n1 p1 tilde t, remember the way I defined p1 tilde t, it was characteristic polynomial divided by this. So I'll get here now characteristic polynomial of t. Now Cayley-Hamilton theorem will say that this is 0. I get 0. So you can see that even if I had taken minimal polynomial, it wouldn't have mattered. I still get this 0. So this is where, so this comes from Cayley-Hamilton. Cayley-Hamilton theorem. So what I do in this equation, the same way I can prove that, so this element is supposed to be in V1 and this element is supposed to be in VR. I have written any vector V as sum of elements from V1, V2, VR. So this also proves that V is direct sum of Vi. I hope this is clear. So what we have proved just now is that V is, we prove V is direct sum of Vi. And the way we have defined this Vi, you can see that if I restrict, so how VIs are defined? VIs are supposed to be kernel of Pi t to power ni. You can see that T of Vi is clearly inside Vi. Because if I take any vector from this, apply T, it will still make 0 because of this is supposed to be a kernel, right? So this is also true. And then I can restrict uh, T to this VIs. And the way I define this Ti, I'll get automatically the other parts. The characteristic polynomial of Ti will be exactly, you see this part, because I have defined it that way. It will be Ti x to the power ni, and minimal polynomial of Ti is Ti x to the power ni. So this proves basically the primary decomposition theorem. And it's a very nice theorem. Let's try to apply this theorem and see what kind of results we can get. So this completes the proof of primary decomposition. Let's apply this theorem. So application of primary decomposition. So application of primary decomposition theorem. First thing is that it reduces the problem of finding canonical form of T to uh, only those kinds of T uh, which have characteristic polynomial and hence minimal polynomial uh, of the form Px to the power some, let's say, k, and Px to the power l. Of course, l is less than equal to k, right? So it reduces clearly to this situation. So, for example, in the Jordan canonical form theorem, I need to only uh, look at uh, matrices where I have only single eigenvalue, because anyway, if there are more than one eigenvalue, that means the polynomial has more than one irreducible factor. So I can apply this primary decomposition theorem to write it as direct sum anyway. So that's the first application. Second application is as follows. What I do is uh, let's look at the situation when. So let's apply to the situation. Uh, Let us apply this to the situation when minimal polynomial of T is of the form x minus lambda 1, x minus lambda 2, and so on, x minus lambda r. right? Minimal polynomial is of this form. What happens if I have some transformation of which minimal polynomial is of this form? That means it's a product of irreducible polynomial of degree 1, and each one of them appear with degree 1 only. So the canonical form, this primary decomposition, so primary decomposition theorem will imply that I can write uh, I can write V as V1 direct sum VR, uh, and Ti, which is basically T restricted to Vi, has minimal polynomial exactly x minus lambda I. But what is the meaning of a linear transformation having minimal polynomial x minus lambda I? This means that Ti is just a scalar multiple, right? So this means Ti is simply lambda I times identity matrix on Vi. This is what it means, right? So this means uh, what does this mean? So this will actually prove the result which we had said earlier, that uh, so this will mean that T is diagonalizable actually. So this will prove the result that a linear transformation T is diagonalizable if and only if minimal polynomial of this MTX is product of linear factors. Product of linear factors. Right? So we prove that result. So in fact, I mean, if you see the proof of this earlier, we can also prove this using primary decomposition theorem quite easily. It just follows as a corollary of primary decomposition theorem. We can also prove Jordan decomposition, which we stated yesterday and earlier in the beginning today. The application 3 is we can prove Jordan decomposition theorem from this. So let's try to do this. So suppose I have, so remember for Jordan decomposition theorem, I have assumed F is algebraically closed. You can take, for example, F equal to C. So I have T in end V. Suppose characteristic polynomial of T is something like this. So X minus lambda 1. Because now I'm over algebraically closed field, so irreducible polynomials are of degree 1. So X minus lambda 1 to the power n1, X minus lambda to the power n2, and so on, X minus lambda r to the power nr. And suppose the minimal polynomial is X minus lambda 1 to the power m1, X minus lambda to the power m2, and let's say X minus lambda r to the power mr. So then I can apply primary decomposition theorem. So primary decomposition theorem implies I can write V as direct sum of V1, V2, and so on, VR. Okay. So from primary decomposition theorem, we get this, and I have Ti, which is T restricted to Vi, and with the property that characteristic polynomial of Ti is exactly Pi x to the power Ni, and minimal polynomial of Pi is simply Pi x to the power Mi. Right. So this I get from primary decomposition theorem. Now what we do, remember in Jordan decomposition theorem, I had to obtain diagonalizable element and nilpotent element, right? So that T is sum of S and N. So I will define S. So let us define S as follows. So remember, S will be also a map from V to V, and V is supposed to be direct sum of Vi. So I will define S also on each of the Vi as follows. So S is from V to V, uh, uh, defined on Vi by, so S restricted to Vi. I will simply take it as the scalar lambda I times identity matrix, identity transformation on Vi. Okay. So this is, so you can see that on S1 it will be lambda 1, on S will be on V1 lambda 1, on V2 it will be lambda 2, and so on, right? This is how I define my S. And this is quite well defined because V is supposed to be direct sum of Vi, so it is well defined. And if you want to think of matrix, if you choose basis of V1, I will get lambda 1, lambda 1, lambda 1, and then lambda 2, lambda 2, lambda 2, and like this. So this is how, if I choose the basis of V1 first, then basis of V2 second, and so on, then the matrix of S will look like this. So in fact, it already looks like a diagonalizable something. So that is very easy to see that S is diagonalizable. Clearly, S is diagonalizable. In fact, on each of the V1, V2, it is scalar only, a fixed scalar. So we have got it in very nice way. And now I have to define N. So let us define N. N to be, so I have transformation T, and I have defined S. Anyway, I am expecting T to be N plus S. So I'll define N to be T minus S, right? And but then we have to prove that N is nilpotent. So claim N is nilpotent. So this is, so once I prove, so I'll prove this claim, but you can see that once I prove this claim, I already have T is S plus N, and I already have proved T is diagonalizable and N is nilpotent. And you can also see that S into N is N into S. The question is why. This is, I don't know whether I should leave it as an exercise, but this is very good way of thinking this. Because I can prove S into N is N into S on each of the block V1, V2, and Vr. If I look at the block Vi, S is just scalar. So scalar will commute on that block with any matrix, in fact. Whatever N is, doesn't matter. So scalars are in the center of set of all matrices. So that is why S into N is N into S. This will automatically come. So all I need to prove that N is nilpotent. So to prove N is nilpotent, we will prove N restricted to Vi is nilpotent. And on each block, if it is nilpotent, then the total thing is nilpotent because there are only finitely many blocks, right? So to prove N restricted to Vi is nilpotent, we know that N restricted to Vi by definition is T restricted to Vi minus S restricted to Vi. And what is the so we can define this to be, let's say, Ni, just for simplicity. And this is supposed to be just Ti, and this is supposed to be Si, but Si is, the way I have defined it, is just a scalar lambda I types identity. So you see that the minimal polynomial of T, the minimal polynomial of Ti was supposed to be x minus lambda I to the power mi, right? And if I substitute in this this thing here, you will let's say T, then you will get here Ti minus lambda I. But this Ti minus lambda I is exactly this supposed to be N, right? This is what it is here. This is Ni. So this will imply basically that Ni to the power this Mi is 0, the same Mi in fact. It could be lower also, but certainly this Ni will work. And this gives Ni is nilpotent. And I have finitely many blocks of nilpotent. So together they are also nilpotent. So this proves Jordan decomposition theorem. You can see that quite easily we can get from primary decomposition theorem these things. So this leaves only okay, it's 6:30, so we still have some time. So we have proved some major things so far already, and I don't know how much more proof we can do, but what I will try to do is that, as I had commented yesterday, that the Jordan decomposition doesn't give you the form of the matrix of T as such. So we have to do better than that, which is what is Jordan canonical form. And Jordan canonical will write every matrix as, so again, this works for F algebraically closed. For example, F could be C. So here we are seeing that T will look like various blocks of kind like, lambda 1, 1, 1, 1, 1, and this kind of blocks, right? This kind of blocks it comes out to be. So how to obtain this nice form? And this part gets slightly tricky. It involves a little bit of complications in a way. What is called finding cyclic vectors. So I am going to just explain what cyclic vector means, and then I will just state the theorem rather than giving complete proof. And then we'll see how to get the canonical form from that theorem. So anyone who knows module theory a little bit will easily understand this part of these definitions, what I'm going to make now. Purely in linear algebra, these definitions look kind of out of blue and very artificial. But if you know a little bit of module theory, it is somewhat easy to appreciate this. Okay. So what we do is that, let's begin with, so now we want to, what I call, now we want to learn what we'll call cyclic vectors or cyclic decomposition. We'll come to cyclic decomposition. So cyclic vectors, right? So this is something what we want to learn. So again, I have set up that I have vector space over field F of dimension n, and I have some linear transformation T in N V. Right? This is what I have. Let's just recall something. So since I have field F and I am given T, I can consider the set of all polynomials over F. So this is a polynomial ring in one variable, and from polynomial ring in one variable, I can define what I call a ring homomorphism. So how do I define ring homomorphism? This will be defined by sending X to T. Which, if I want to write more explicitly, then some polynomial fx, which is, let's say, a0 plus a1x plus a1x to the power n, I will send this to f of t, which is a0 plus a1t plus so on plus an t to power n, right? So this is how I define it. Let's give it a name. Let's call it phi t. So you can see that phi t is a ring homomorphism. Ring homomorphism, right? Because if I have two polynomial fx plus gx, you can see that this side it will get additive. If I have polynomial fx into gx, f of t into gt, you can check easily that it's a ring homomorphism. Now, what does that mean here? Uh, so we want to get into the context. So first thing, notice this, that phi is not injective. It cannot be injective. And why? So the easy answer to this, is this, that if it is injective, you will see that on the left hand side, fx is infinite dimensional over f, whereas endomorphism of V, which are matrices, n by n matrices over F, so it is only finite dimension, n square dimension. So that's very easy way of saying that it cannot be injective. So since it is not injective, it must have a non-trivial kernel. So we can have kernel of phi t. It must be non-trivial, and since it's going to be an ideal in the polynomial ring, it will be generated by some polynomial. That polynomial we call it to be the minimal polynomial of T. So this is taken to be monic, and this is what is called minimal polynomial. This is the definition in a way of minimal polynomial, right? Now I want to elaborate a little more this concept, and I will, if once again, if anyone knows module theory, you can see that what I have done is that I have made V into fx module via T. But anyway, I'm not going to elaborate too much on that, but it is somewhat easy to see that what we have done is that somebody who knows module theory, so I'll put a star here, that V is fx module via T. Okay. So what I do now is that uh, I I define slightly different map. So now I take a vector V in V, fix a vector V in V, and uh, I want to define a map fx cross V to V by taking any polynomial here fx, uh, and you can evaluate. You should take a vector V here. I can send it to f of t evaluated at V. Okay, so keep this aside. So what I'm going to do is that, given a vector V in V, I'm going to define uh, a subspace. I can give it a name. So let's call this as ZV T. This is supposed to be f of t applied to V for any polynomial fx in fx. Okay. So what I do, I take some vector. If you take zero vector, you will get only zero. You can take if you take a non-zero vector V. Certainly, I have vector V in this set, right? Because of course I have the constant polynomials, and then I have other polynomials, and I apply them each one by one. I take ft of V, and then I just evaluate on all possible V. You can also see that this set actually can be thought of spanned by V, T, V, T square V, and so on. If I take all this power, I can think of subspace spanned by this. This set is also can be thought like this. But we know that there cannot be infinitely many such things because our vector space is finite dimensional. This is, after all, subset of V, right? And these are, you can check that this cannot be infinitely many, because if I want to write a basis for this subspace, whatever the subspace is, it has to be finite. So these numbers cannot be also infinite, and that will lead to getting what you call annihilator of this vectors. Annihilator of V is going to be, let's say, those polynomial gx such that gt applied to V is 0. And again, you can check that this is an ideal and things like that. And this will actually relate to the dimension of this ZVT, whatever I defined. Okay. So what is the relevance of ZVT? Here is the definition. So we say V is T cyclic. So this vector space V is T cyclic if there exists a vector, let's say V naught in V, such that uh, ZV naught T is equal to V. And the relevance of ZVT, the cyclic subspace, is quite interesting. Let's try to understand that. So let me write this as a lemma first. So a lemma. V is T cyclic if and only if the minimal polynomial and characteristic polynomial are same. All right. This can be proved quite easily. I will leave it for you to try this out. Prove this. This is not difficult. You can prove this yourself. And the final theorem is this, that if I take any t in end v, then v is a direct sum of finitely many t cyclic subspaces. Okay, that is to say, that is, there exist some vectors v1, v2, vl, such that v is z v1 t direct sum z v2 t direct sum z vl t. So the proof of this theorem is a little bit involved. It takes some time to prove this, so I'll not prove this. Instead, we apply this theorem. We see how to apply this theorem and how to get the result what we want, right? So let's apply this theorem. Application of this theorem. Anyone who knows module theory will also see again the cyclic is somewhat very easy there. Is just a submodule generated by one vector. That's what is cyclic. One element of the module. That is what is cyclic, and it's very easy to think from that point of view here. So, what is the significance of getting this? What we are trying to say cyclic, right? So suppose I have a vector space V, which is T cyclic. What does this mean? I mean, my claim is that you will get a very nice matrix whenever you get a T cyclic vector space. That is why this is very important. So let's try to understand this. So when I said that V is T cyclic, that means there exists some vector V in V such that V is basically spanned by some finitely many V, TV, T square V, and so on. Let's say it is T to power k minus 1 of V, right? But since I am saying V is equal to this, better k be equal to N, right? N is equal to k. So this there are total n vectors here. Now, if I take this as a basis, take this as a basis. and we try to write the matrix. For the linear transformation T. How does it look like? So first of all, we set this notation. Chi Tx is the characteristic polynomial of T. Let's say it is C0 plus C1 x plus C n minus 1 x to the power n minus 1 x to the power n. And now I want to write the matrix of T with respect to this basis. So how do I write matrix? Let's do this. So to write the matrix, we compute T of these basis vectors one by one. So T of V is simply T of V. So this is just 1 times T of V. T of V, it is basically 1 times T square V, right? So so this happens up to, if I apply T up to T to power n minus 2V, I simply get 1 times the next basis vector, which is T to power n minus 1V. But if I apply T to the last vector, T to power n minus 1V, something different happens, because this will become T to power nv, because T to power nv is not a basis vector. So how do I get T to power nv? Then I use Cayley-Hamilton theorem applied to this characteristic polynomial. From here, you'll see that T to power n is chi T of T is 0. So T to power n will become combination of these things here, right? So you'll see that this can be written as minus C0 V minus C1V, C1T of V, and so on, minus Cn minus 1, T to power n minus 1 of V. So now I written it as a linear combination of basis vector. Now the matrix of T with this basis would be, so the first column is going to be 0, 1, 0, 0, 0. Second column will be 0, 0, 1, 0, 0, 0, and so on. Last but one column is 0, 0, 0, 1 here. So it will go like this. So 0 is on the diagonal, 1 below the diagonal. And the last column here will be minus C0 here, minus C1 here, and so on, and minus Cn minus 1. I'm sure you will recognize this. This is what is called companion matrix of that polynomial. So this turns out to be companion matrix of the characteristic polynomial, right? So this is what happens. So significance of finding a cyclic vector is that you can actually write the linear transformation on that subspace as its companion matrix. Let's try to apply this to get Jordan canonical form. So now the second application will be, so remember, for Jordan canonical form, we have F algebraically closed. So algebraically closed. For example, we can take F equal to complex number. So for Jordan canonical form, the characteristic polynomial is supposed to be x minus lambda 1 to the power n1 and so on, x minus lambda r to the power nr. But I can apply primary decomposition and I can look at only one component. So let's assume, without loss of generality, I can assume that chi tx is a single polynomial x minus lambda to the power whatever I have, n1 or n, doesn't matter. I can take just n, right? Now what I do is that I can write this as a, so the theorem implies that V is direct sum of some cyclic vectors, Z, V1T, direct sum, Z, V, R, T. And let's say this is of, so now I want to write, let's say this is of dimension, maybe, just for simplicity, let's call it N1 and NR. So I want to write now the matrix here. If I want to write matrix here, Let's say this corresponds to x minus lambda to the power n1, and this is x minus lambda to the power nr. Then I will try to write this matrix here so that anyway it is direct sum, so you can do on the other block. So I'll choose the basis as follows. I will choose the basis as this vector v1. I have v1 here, and then I can do t minus lambda v1, then t minus lambda uh, square v1, and so on up to t minus lambda to the power n1 minus 1 of v1. And let's write the matrix with respect to this, right? So, okay, yeah. So T of V1, but T of V1 is not a vector here. So I have to write as a combination of these vectors here. So what I do is that I write T minus lambda plus lambda of V1, and this will be lambda V1 plus T minus lambda V1. And then similarly, I do for the second one, T minus lambda V1. Again, I do the same trick, and then I write it as a, here I write this one as T minus lambda plus lambda. So you'll get lambda times T minus lambda V1 plus T minus lambda square V1, right? This is what you get until you reach the last one. When you reach the last one, if I apply T to T minus lambda to the power n1 minus 1 V1, you'll see that I'll get lambda times T minus lambda to the power n1 minus 1 V1 plus T minus lambda to the power n1 of V1, but this is 0. So if I write the matrix, so the matrix on V1 block, this is going to be, so look at the first one. I'll get lambda here, 1 here, and then 0, 0, 0. Then the second one will give 0, lambda 1, 0, 0, 0, and so on. So you'll see that on the diagonal, I'll keep getting lambda. Below the diagonal, I'll keep getting 1. The last one you see, it gives me only lambda. So this is the Jordan matrix. Although I have got in the lower triangular form, they matter. You can reverse the order of the basis and you will get the upper triangular form. Then it's not much difference. So we get Jordan matrix. So combined with the decomposition theorem, the primary decomposition theorem and cyclic decomposition theorem. So primary decomposition theorem together with cyclic decomposition, which I said above, give me Jordan canonical form. The way I have stated all these things, it's much more general. You can actually get the rational canonical form also, because I said that you get companion matrix. So you can also do the next application that you can actually get what is called rational canonical form. But I'm not going to elaborate too much on this. Rational canonical form is that where you don't need to assume any condition on f. F is anything. But then in this case, now you may not have eigenvalues. So you will not get this kind of nice matrices. Instead, you will get block matrices where companion matrices will appear in the blocks. So that statement is slightly complicated to write, so I will not write there. There is not much time. Instead, if you have some questions, you can ask me now. You have a few minutes. So I will stop sharing. You can ask any question.
Sir, the way you
Yes.
have given the proof means from algebra point of view. So, sir, I want to ask you where I can find all these things. Which book or
Yes, yes, yes. I mean, most of the books do it also this way. So even the Hoffman Kunj has this kind of this proof, or uh, maybe I'll write a list of books maybe tomorrow or day after tomorrow, where I'll point out exactly where you can find these proofs.
Oh, thank you, sir. It would be great.
Yeah, yeah, yeah. Some reading
And
material and some yes.
yes, sir. Please share these this notes PDF
Certainly,
means
yes,
if
yes, I
we
can because I'm writing here, so I can as well share PDF of this. Maybe I will send it to Dr. Dilpreet Kaur,
Dilpreet
and
ma'am.
yeah, she can share with you.
Great, sir. Great. Thank you.
Yeah.
Any other question? If not, shall we end this call here?
Yeah. Thank you.
Uh, thank you, sir.
Thank
For
you. Thank you, everyone.
tomorrow
See
we
you
have two
tomorrow.
lectures,
Yes. Okay. And
1 hour
the
each. Yeah.
okay.
Sorry.
So it is
So
at 5 o'clock, right? Or
yeah,
it
the
begins at
first
5.
talk is from 5 to 6. The second is
Okay.
from 6:15 to 7:15.
Okay. Sure.
So
See you
I'll share
tomorrow.
link with all of you. Okay.
Sure.
See you
Okay.
tomorrow. Bye.
Okay.